edit different dynamic programming problems. So this matches the second case here. So you have two inputs x and y, and the subproblems correspond to prefixes of the two inputs. So that's exactly how we are going to formulate this here. Okay, so so the way we are going to do this is we are going to go left to right. So we are going to use E of I comma j, right? E stands for the edit distance. I comma j says, captures the prefix on which we have already worked, right? So in this case, for instance, we might have computed the edit distance between this prefix that consists of these 7 letters with this prefix which consists of 5 letters, right? And then using that edit distance, then can we compute the edit distance of, let's say, these 8 characters with these 5 characters, right? Or these 7 characters with these 6 characters, right? So either way is something that allows us to make progress going left to right on at least one of the 2 strings. Okay? So once again, keep in mind, so I denotes the prefix of x, and j denotes the prefix of y, right? So when we say E of ij, we are talking about the edit distance of the prefix x1 through I with the prefix y1 through j, right? So keep that clearly in mind. Okay, so now we said that how from the shortest edit distance between 2 prefixes we can compute or go to the next step, right? So in particular, what we want to do is we have computed for these 2 prefixes, right? So we want to, let's say, extend this by 1 more character, right? So that is what we would call as E of k comma L, okay? So there are 2 ways, right? So let's say you already know let me expose the whole slide. That will make it a little bit easier. Okay, so the edit distance, as you remember, allows you to take a string x and convert it into a string y, right? So now what we already know so far is the 3 cases, right? So if you think about, let's say in the previous case, right? So we have, let's say, okay. So once we have computed all of these values, okay, that's when we are going to try to compute okay. So as we said, we want to go left to right, which means that to go to k comma L, you should be able to go right by 1 character on x, the prefix of x, or right by 1 character on the prefix of y, or simultaneously increase both by 1, right? So in this case, what you're doing is you're including 1 more character from x, because you're going from k minus 1 to k. In this case, you're including 1 more character from y, going from L minus 1 to L. In this case, you're including 1 more character from x and 1 more character from 1, right? So that's why you go from k minus 1, L minus 1 to k comma L, okay? Now suppose you already know what is the edit distance, right? The value of this, right? So what is the smallest cost sequence that maps x 1 to k minus 1, right, to y 1 to L, right? Suppose you know that, right? So one way to compute, so from this, what you want to compute, okay, how do I go from right? So this is the edit sequence you want to compute. Suppose you know this already, right? So then what you need to do is you just need to do one more step, right? So you already have your way of getting to y1 comma l from there, right? So what you can do is right? So you have a way of going from the prefix up to k minus 1 to here. Now if you add the operation delete the kth symbol, then this converts into a sequence that will take this to this, right? Because the only difference between this and this is that this has the kth character. Now, how do you get rid of the kth character? You delete it, right? So now the kth character has been eliminated. Now what you have ended up should match y at this point, right? So this is one case. Similarly, so that's what we are saying. Extend this edit distance from this edit distance, derive the edit distance to the prefix up to k by deleting xk. Alternatively, what you could do is you could start from here, right, and then say I want to insert a character, right? The lth character of y could be inserted, and so in that case that corresponds to this. Or you could be trying to put both of them at the same time, which means that you are trying to substitute the kth character of x with the lth character of y, right? So these are the three cases to consider, and because you want to minimize the cost, you're just going to take the minimum across these three cases, right? So so again, this is the cost of the edit sequence that you have computed so far. If you're starting with the prefix of k minus 1, and then you add the deletion cost of x of k, that corresponds to this case. Similarly, here you are adding the insertion cost of y. And here, because you are going from e of k to x of k to y of l, so you are trying to find what is the cost for substituting x of k with y of l. Okay, so those are the three cases. Now, in the picture that we'll see the next slide, these each of these choices corresponds to moving right, down, or diagonally right in the matrix of edit distances, right? So this E is a matrix, right? So it's a two-dimensional array. So you're going to have, so let's look at that. Okay, so the array is shown here, and it is filled out, right? So of course, we haven't gone through how to fill out that array in its entirety, although the formula is just this, right? So this is the formula that's used to fill that out, right? So what we say when we say we are going down, right? So we are going here, right? And this refers to the right direction, and this refers to the diagonal direction. So what do these things mean? So down here means insertion. That is, basically what you're doing is you're not, so you can see going down means you are increasing k, right? And okay, so this is going to the right and
Going diagonal.
yeah, so because you see that this k remains the same, right? Which means which is the row, right? So if the row remains the same, that means you are just increasing the column by 1, right? So that is why this is a horizontal. Here you're increasing the row. So k minus 1, you're going to k, right? So therefore you're going down. Here you're increasing both of them, which means that you're going down by 1 row and 1 column, and that's why that's shown as a diagonal. Okay? So now So what we are going to do is we are just going to, so we have set up this equation that says how do you compute the optimal distance EKL from those three quantities, right? Now, in order to set this all up, we also need to define what is the base case, right? So E0L, so what is E0L? E0L means you're matching the empty prefix of x, right? Because the first one says 0. So you're matching the empty prefix of x with prefix of y that has L characters, right? So because you're starting with the empty string, the only way to get to y is by inserting all of the characters into this empty string, right? So as a result, you have E of 0, L is set up to be the insertion cost of every character in y, right? Because you're only going up till the Lth character in y, the summation is also only up to the Lth character. Okay. Similarly here, what you are doing is you take a prefix of x that's of length k, and then you are trying to convert it into prefix of y of length 0, which means that you have to basically delete all the characters that are already in x1 through k. So you apply the delete cost of x1 through xk, and that's this summation. Okay. So once you define the base cases, so what that means in this array picture is that you have defined the first row and the first column, right? So the very first row says, right, so this array has been filled under the condition that insertion cost of any So for any two characters, alpha and beta, insertion cost and deletion cost and substitution cost, they're all same. Okay? So that's just a simplifying model, right? And so that means that's why you have the row values just increasing by 1, right? Because if you are talking about 0, 0, that means you are matching the empty string against itself. So the cost is 0. The moment you introduce one character in x, now to get to the corresponding, so these rows are simply being initialized. The first column and the first row are being initialized using this formula, right? And because all of these costs IC of yi is all equal to 1, that means as you go to the right or as you go down in the first column, the values are going to increase by 1, right? So that's why you have 0 through 10 and 1 through 0 through 11. Okay. So now we need to see how this thing is going to work. So now we'll try to compute. Okay, without, for the moment, right? It's easier to ignore the numbers that are in there and just see how the computation proceeds. Okay. So when we are in this picture, so as we said, all of the costs are same with one exception, right? If the characters actually match, then the substitution cost is going to be 0, right? So, so for instance, right here, right? So you have the next character is n, right? So it's n being matched against n, right? So if you have some cost to go from that takes the first 6 characters and maps it into the first 4 characters over there, or vice versa, then to extend those prefixes by 1, you don't have to do any, you don't have to incur any cost because there is already a match at the next letter, right? So what happens here is that those cases where the characters already match, then you'll have a dashed edge there, okay? Everything else, every other edge corresponds to a cost increase of 1, okay? The dashed edges correspond to a cost increase of 0, okay? So, so you can see that there are, a few edges where there is a match and the costs are 0, but otherwise you have a cost of 1. Okay. So now let's trace through how we get here. So we are starting from the empty prefix. Then we see E. There is no match in the we see E in the second string, right? There is no match for that in the first string, so we have to delete that. So we go down, okay, and then we delete. I'm sorry, that's called insertion, right? Yeah, it's called insertion. Okay, so we are inserting E to get to the string Y is spelled vertically here, and the string X is spelled horizontally. So to go from X to Y, you have to first insert the two characters E and X, okay, and that's why you go down from here and here, okay, and remember that although I'm going to show you why this path is correct, right, or why this path makes sense, right, I'm not really computing the whole array, right, because that will take forever. Why this is the best choice as compared to all of the other choices, that's something that you will have to sit down and see for yourself. Okay, so for instance, you could say, why should I insert E? Wouldn't have been reasonable to just delete P, right? And that's fine too. But the problem is that if you do that, if you follow the path, eventually you will find that the cost of the edit sequence is greater, whereas if you choose to delete these two characters, rather insert these two characters here, then you will have a lower cost, right? And it's all about, see, the only place where you can get a zero cost is when characters line up, right? So you want to do insertions and deletions so that the characters will line up, right? So that is, so for instance, you see that the third character, right? So this P and that P are going to match, right? So to get those two P's to line up, you have to do those two insertions, right? If, on the other hand, if you just went right, then you wouldn't find any matching character in the other string, right? So that's why it ends up following this path. So now, after inserting the two characters E and X, now you see the third character of Y matches the first character of X, so the two are matched. So you take the diagonal transition, and then you see that the next character is O in both strings, and once again you take the diagonal transition. Following is, you have L and N, right? So they don't match, but still you end up going to the right, because as it turns out, the shortest path happens to follow this. And then the next character also doesn't match, Y and E, but then you have N, so N's match, so you go through the zero cost. And now, once again, you have characters that don't match, but as it turns out, the transition that you choose is one that deletes O, and then you go in the diagonal direction, and now you have I and A and L, all three characters match, right? So you follow this, and now you can see what is the cost of the whole sequence. So the dashed arrows have a cost of 0, so it's the solid arrows that you have followed. So that is 1, 2, I'm sorry, 7. 1, 2, 3, 4, 5, 6. Where is the seventh one I missed? 1, 2, 3, 4, 5, 6. Yeah. Yeah. So, yeah. The edit distance is 6. Okay. So this is again, you have to sit down and try to calculate this, and you probably would like to use smaller strings than this, right? Because I know the answer already, so this string works. But if you have to, calculate it, then you probably want to start with something that has, 5 or 4 characters each, and then you will see. Okay, so now, so this is how you calculate the edit distance, and the minimum value that you get here is actually the edit distance. Okay. Now, the actual edit sequence is found by essentially, keeping track of the path you followed, right? So in this case, the path you followed is being identified by these dark circles, right? So if you keep track of the path you followed, or in other words, each time you compute the minimum, you keep track of which of the three neighbors contributed to the minimum, right? So in this case, so this entity contributed to the minimum cost of this, so that is defines the edit operation at this stage. Okay. Similarly, this one, the predecessor is this, and so on, right? So you keep track of that, and once you keep track of that one, at the end you can just go here and then follow these predecessors, and that tells you exactly the edit operation that you used, right? And once again, remember, this is a substitution operation, and this is insertion, and this is deletion, right? So that's how you construct the edit sequence after you compute the minimum edit distance, right? And the minimum edit distance, remember, always going to be in E of m comma n, right? Because you want to take the entire x, which is x1 through m, or is it n? x1 through n, I think. I don't know which is n and which is m. Let's see. Yeah, so LJ. Okay, so one of them is m and one of them is n. We'll figure out what it is later. Okay, so right. So x goes from 1 to m, and y goes from 1 to m. Okay, x has the length of x is m, and the length of y is n. Okay, so now now that we know how to do edit distance, we can ask for some variations of the problem, right? So what if you don't want to do an approximate match of the entire strings, but instead you want to do approximate prefix? Okay, so approximate prefix means that you are willing to discard characters in x after a particular k, right? So we don't know what the k is, because we would like to pick a k such that the edit distance between the prefix and y is minimized, right? So that's why this is the way you identify or compute if y is an approximate prefix of x, and if so, up to what length you have a match. Okay, so once again, the reason why it is EKN is because you want to match you want to match all of y, right? So that's why you're going to go all the way up to n on y, but you want to take only a prefix of x, right? So that's why you're going up to k. Yeah, go ahead.
How do we handle types when we are doing calculating
So we arbitrarily pick. It does not matter, right? Because obviously the edit distance in when there is a tie, it just means the cost is same in no matter which way you go.
But further, it will make a difference, right?
No. Right? Because all we are doing is we are propagating forward, right? So for instance, right? Yeah, so I don't have an example here, but the point is that, let's say you could get here either following this or this, right?
Yes.
As long as the cost here is the same, right? It doesn't matter, right? So what's going to happen to the right of this is not, it doesn't depend upon how you got the value over here, right? You have some value here, and when you're here, you're going to pick the min of these three, right? And all that matters is the value that's sitting here, right? Where this value came from is not relevant, right? It's only relevant at the end when you want to figure out the edit sequence. You need to know how you came there, but if there are multiple ways to come there, that's okay, right? So all of them will correspond to in edit sequence, right? And then again, you realize that the edit sequence, edit distance does not define a unique edit sequence, right? So obviously there could be multiple edit sequences, all of same cost, that take you from X to Y. And when you have a tie, what that means is that depending upon how you break the tie, the edit sequence that you compute may be different, right? Which may be why you are, which may be what you are thinking about, that somehow there is a difference because the edit sequence itself is going to be different, which is true. But it doesn't matter because all we care about is computing the minimum edit distance.
Okay, so I'm confused. Now, if I'm from the beginning, do I choose to go to which one of the three nodes that are adjacent?
No, that's not really how you do, right? You always go, you are here, right? From here, you look to these three places, right?
Oh.
So, and then pick this plus one, right? Or this plus one, or this plus one or zero, depending upon whether there is a match or not,
Oh.
right? So,
So we are going backwards.
no, we are computation proceeds forward, right? So after, what you are calling as backward is the definition of forward, right? Because once these are known, I can calculate this, right? That is the meaning of going forward, right?
Yes, but I don't know what is backward. I mean, I will start from.
Obviously, you start from there, right? So you first compute the first column and the first row, right? And then you will compute 1, 1, right? And then you can compute. So essentially, what you can do is that once you compute the first row, right? Then first column, then you are ready to compute the second column, right? Because 1, 1 will depend upon the three elements around to the left of it and above, right? So similarly, say for instance you're here, you compute this, and then you come here. By then, you have already computed all of these, and then you also finished computing this right now. So you're going to compute this next. So you're going to go this way, or you can just go that way and that way and that way, right? So either you can go row-wise or column-wise, but essentially you are going somehow from the left top corner to the right bottom corner.
So we are computing the whole table?
Correct.
Oh.
Correct. Otherwise, how do you cannot figure out, right? So in this formulation, right, so you have order of mn subproblems, and you have to compute the solutions to all of these subproblems before you know the final solution. Yeah.
So what if the number of operations increases?
What do you mean increases?
So there are only 3 operations here. We go to the right, left, or bottom.
Well, we have defined that. Okay, it's hard to see what other operations can be there.
Let's say we invent some hypothetical.
Yeah. So we'll talk about some variations before, but it is pretty clear that these are the to go beyond these 3 operations is a little bit of a stretch, right? So this is the most obvious set of operations.
But my question is, would that affect the algorithm?
So let's get to the variation, and then you'll have a little bit more of a basis, or we'll have more of a basis to answer that question. Okay. So here, so the algorithm we discussed so far computes the distance of 2 entire strings. So now what happens if you are only interested in a prefix? Then you're going to take the prefix of x up to k, right? And then you're going to take the entire y, which goes up to n, and then we're going to say, okay, what is the edit distance? Okay, and because we want to find the prefix that minimizes the edit distance, that should be min, right? Okay, so it should be the min of the across all of those k, and then that'll tell you whether there's a prefix, and if so, how long is that prefix? Okay, so if you want a suffix, okay, then this is what you do. Okay, you have to change the initialization a little bit. right? Because you want a suffix of x. What that means is that you need to say, I'm willing to drop any prefix of x without matching anything, right? So because I'm only interested in a suffix. So I'm going to be able to drop any prefix of x without a cost, and that's what this is saying, right? I can essentially delete the first k characters of x, and the cost is going to be 0. Okay, so this means that the the first column, right, or rather the 0th column here, right, in this setup where we are trying to match the entire character, entire strings, the first column consisted of 1, 2, 3, 4 up to 11. What we are saying here is that if you want to look at the variant that we just discussed, this column will become 0. Okay, which basically says you are free to drop any prefix. Right? So to match a prefix of x of length k with the empty string costs nothing, because the empty string is always a suffix of any string. Okay, so now we just pick e of m comma n. That tells you the edge distance. Okay, because we are just doing the same. We run the same algorithm with just a slightly different initialization to accommodate the fact that you are allowed to drop any prefix of x. Okay, and then now you wanted to approximate substring. Then what do? Right? So we know how to do prefix, we know how to do suffix, then we should know how to do substring, right? So how do we do substring? The answer cannot be any more obvious, right? I mean, okay, that's a hint, right? This answer cannot be any more obvious because the answer is already in front of you. Right? So what is a substring? That means we are willing to drop a prefix and we are willing to drop a suffix, right? So the first one says approximate prefix. What that says is that I'm willing to drop any suffix of x, right? So the second problem says I'm willing to drop any prefix of x, right? So now you're going to say I'm willing to drop any prefix and any suffix of x, right? So therefore I just put these two together, right? So I do this initialization, which allows me to drop any prefix of x, and then I pick this entry e of k comma n such that this is again should be min, right? And that way I get the substring that matches. Okay, so the problem of doing approximate substring can be solved using the same algorithm, and the cost is the same, O of mn, right? And that it is O of mn is pretty clear, right? Because you have this array, m by n array that you are filling out, right? And to fill out each, say this cell, you only compare with 3 elements, right? So therefore filling each cell requires only constant time, and therefore the total runtime is simply proportional to the size of the array. And so for the original array distance problem as well as these 3 variants, you have O of mn algorithm. Okay. So the variation, so this here is a variation. So now you allow transposition, let's say. Okay. Obviously, if you're thinking about spell correction, right? Because of how we type, transpositions are much more likely than, say, 2 insertions and deletions or something like that. So when you have transposition, because that involves 2 characters, right? So now you have to change the distance, change the computation a little bit differently, because the transposition allows you to go right, switch 2 characters, right? So basically what you have is you want to allow, say, AB to match BI, right? So in order to do that, you have to jump from a prefix of this length to a prefix of that length, right? So you have to jump up by 2, right? So that's so now you have in addition to the 3 neighbors in the matrix, you also have to look at neighbors that are a little bit farther away, right? And then you'll get. And now also you have to define what is the transposition cost and so on. Okay, so similarity versus edit distance. So one of the things about edit distance is that the number itself doesn't tell you how similar 2 strings are, right? So the example that we looked at, exponential and polynomial, the distance was 6, right? The 2 strings don't look similar, right? So we would say that they are not similar, but if let's say I give you 2 strings, each of 1,000 characters long, right? If the edit distance is 6, well, you would say these 2 strings are very close, right? Very, very close. So similarity is another way of assigning cost such that when the strings are similar, you will get a large positive value. Whereas if they are, if they are very different, you might get a large negative value, right? And so the similarity metric will tell you more about how close the 2 strings are. Okay, so it's just as far as the distance is concerned. I mean, it's just a slight variant, and because similarity is going to be a positive thing, you're going to use max here, right? In the other case, we use a min. Now we are going to use max because we want to pick the most similar sort of transition. Okay. Otherwise, this is quite similar. As I said, the costs are negative, right? The costs are going to subtract from similarity, and when you have the when you have the 2 characters matching, then you have an increase in the value. Okay. So thinking about it in this way doesn't really make any difference to the algorithm and so on. It's just a different way of looking at assigning cost, so that at the end the number is easier to interpret. Okay, so it's really not, you don't have to worry beyond that, right? It's just a different metric that is a little bit easier to interpret at the end. Okay, so I'm not going to talk too much about global alignment and local alignment and so on. If you happen to take a course in computational biology or something like that, you will hear a lot more about applications of edit distance and various other string matching algorithms in biology. But I'm not going to talk about it beyond what we've already said, which is that looking at if you want trying to find the similarity between 2 strands of DNA, you can use edit distance to do that, right? So that's the exact match on strings. Well, that won't work very well, but edit distance works very well. Okay, so now we already said that the cost, the runtime is O of mn, and because we are constructing this array, the space requirement is also O of mn. Okay, so generally O of mn quadratic time is often something that you may be able to accept, but quadratic space is often far too large. So you would prefer algorithms that don't require that much storage, right? I mean, if you think about say DNA alignment, right? So you could have like million long strings, and then 10 to the power 6, m is 10 to the power 6, n is 10 to the power 6, right? So you have to worry about storage of the order of 10 to the power 12, right? So which is terabyte, right? So that's a lot of memory. So it becomes hard to do this. Now, as I said before, right? In filling out the matrix, right? I said you could either fill out the first column and then the second column and third column and fourth column and so on, right? And that way of thinking about it tells you immediately that to compute this column, I only need the previous column, right? So I don't have to store all of the other columns, right? So that tells you that to just compute the edit distance, right, you don't need to store all of the array in memory at a time, right? So you can compute the first column, then you compute the second column. When you compute the third column, you can reuse the storage that you already assigned for the first column, right? So in fact, you can do with storage of O of m plus n, right? But the problem is that in the end, after you have computed the edit distance, right? Remember, to actually construct the edit sequence, we needed to know which way we came, right? And so that means we need to really store the entire array, or else we won't know how to trace back. Okay, so this is sort of the problem, and there are actually people who have thought about this and developed algorithms that that use linear space but still can construct the entire edit sequence. Okay, so but the algorithm gets, the algorithm that we discussed so far is so simple. This one gets much more complicated, so we won't really talk about it. So it's not that the algorithm is conceptually difficult, but in order to just get it to work, it's a lot of material to get through. So I won't worry about these formulations that can work in less than quadratic space. Okay, but again, all of them take quadratic time, right? So that they are not improving on. It's just the space that you can reduce. Okay, so why do we care so much about edit distance? So all of you have used this application called diff, right? So what does diff do? Diff uses edit distance. Okay, so how does it do edit distance? Not in the most obvious way that you might think of. What it does is it takes a single line, right? A line that ends with a line feed or carriage return and line feed, and then it hashes that whole thing into one value, right? And then it thinks of this hashed value as one super character, right? So either two lines match in their entirety as far as diff is concerned, or they don't match at all, right? They are completely different, right? And this helps in two ways, right? So one of them is that when two lines line up in their entirety, right, then you have much more confidence that that match actually means something, right? Otherwise, let's say you have a variable name called, ABC, and another variable called, AC, right? Well, maybe the edit distance is small. That doesn't mean that they are, very similar, right? Or, you can think of many examples in programs where even small changes are significant, and therefore, because diff is primarily used on things like programs, right? So it works much better when you have when you're looking at entire lines. Okay. So another reason why you look at lines is because that cuts down the length of your strings, right? Because now your string has the length equal to the number of lines in the file, right? Because each line is being converted into one character. So your m and n become much smaller, right? Because you can imagine that lots of files could be 100,000 bytes, right? If you want to do a diff of 200,000 byte files, it's going to take 10 to the power 10 time, right? So that's a long time, right? So you don't want that. But if you look at it in terms of the number of lines, probably it has only 2,000 lines, and now it's only 1 million and not 10 to the power 10, and so you can actually get done much faster. Okay, so for all these reasons, diff tends